Hey guys, okay, so I received another request for, I'm just going to do u-substitution because I know that's the most difficult, and I thought you guys had it, but I did receive another little email from somebody who asked me to upload a video, so here it goes, u-substitution. We're going to use this substitution method with composite functions. So in other words, a composite function in your integrand is going to contain a radical with stuff going on inside, e raised to, the 2x, 3x, negative 1/2 x, whatever, just things, right? Stuff. 2x plus 1 to the 6th, let's say, or 1 over a radical. So denominators, parentheses, exponents, radicals, these are the things we're going to look for when we use u-substitution. And what you're going to do is you're going to identify the inner function and you're going to let that be your u. And then you're going to find the derivative of that inner function with respect to x. So this is your Leibniz notation, du dx. You're going to rewrite the integrand using u and du. And then you're going to integrate the outer function only, recompose it with the inner, and add plus c, because you never can ever forget the plus c. So best learned by example. So here we go. Here's a simple one. Here I have a composite. I have parentheses with stuff going on inside. So my outer function is x to the 5th. So my inner function is x plus 3. So that's the thing I'm going to call u. U is equal to x plus 3. And when I take the derivative of u with respect to x, so I'll write it this way, but again, as I mentioned in class, we always move the dx over by multiplying both sides by dx. The derivative of this thing with respect to x is just dx, right? It's just 1. So when I multiply both sides by the dx, I really get du is equal to dx. Okay, so that's why in class I don't write it this way, I just say du is equal to 1 dx. Okay, so you can do that too. Alright, so now we've got to create our integral containing u. So we have this integral. So since this whole thing is u, it's going to be u to the 5th, inner function to the 5th. And since dx matches that, I'm going to replace my dx here with du here. So now everything's in terms of u, and this is easy to integrate. If I integrate this, I get u to the 6th over 6 plus c. And now if I back substitute my expression for u, I get x plus 3 to the 6th over 6 plus c. Okay? Or you can write it, if you wanted to, as 1/6 times x plus 3 to the 6th plus c. Now if you take the derivative of this result, you should get back the same integrand you started with. So let's do that. If I take the derivative, right, this is chain rule. I'm going to bring down the 6, so I have 1/6 times 6 times x plus 3, we subtract 1 when we take a derivative, to the 5th, times the derivative of the inside. The derivative of the inside is 1. The derivative of a constant is 0, so we leave that off. And if I clean this thing up, the 6's are going to cancel, and I get x plus 3 to the 5th. And that is exactly what we started out with. So you can check your work by taking the derivative of the result. If you get the same integrand back, then you're in good shape. Okay. Another type that's a little bit tricky because it doesn't look like an inner or an outer function, and I know we went over this in class, would be the sine of x, say, times the cosine of x, times dx. So when you have something like this, you got to be very careful. If I let the sine of x be my inner function, that's my u, and I take the derivative of the sine is the positive cosine of x dx. And guess what? That cosine of x dx is sitting right there. So what that tells me is I can replace this with u, and I can replace all of this with du. And so if we integrate this, we're going to get u squared over 2 plus c. And again, back substituting, I get sine of x quantity squared over 2 plus c, or you can write it as sine squared of x, same thing, over 2 plus c, or 1/2 sine squared of x, whatever floats your boat, they're all right. Okay? So just be careful with these, because you don't see the parentheses or the radical or an exponent or whatever. Let's see, I'm looking in your book here. Okay, another example would be integral e to the sine of x times cos x dx. Okay, so I can clearly see I've got e to the stuff going on, so I'm going to let sine of x be my inner function, so u is sine of x. When I take the derivative with respect to x of this little function u, or expression u, I'm going to get, remember the derivative is the positive cosine of x dx. This matches this. I have e to the u, so now I'm going to write my new integral, e to the u du. And the antiderivative of e to the u is just e to the u plus c, because remember, we're integrating this outer function. And if I back substitute, I'm going to get e to the sine of x plus c. All right, let's do another one. Let me just change my paper here. Alrighty, so how about maybe we have integral of x over x squared plus 1 dx. So now I have a denominator, and that's the first thing I want to look in. I'm going to let u equal to my denominator. My denominator is going to be the so-called inner function. And again, you can rewrite this if you want to as 1 over x squared plus 1 times x dx, right? This is 1 over this thing, and this is times x would be x over x squared plus 1. So anyway, if you write it this way, if you sort of break it apart that way, sometimes it helps you see the du and all of that. So anyway, the derivative of this thing is 2x dx. Now here's the issue. I have an x dx. I don't have a 2, so we're going to compensate. Uh-oh, I'm out of focus. Let me try and fix it. Sorry, guys. There. I hope the whole thing wasn't blurry. I wasn't paying attention. But we're going to compensate by, again, we want to make what's in here look exactly like this piece of the puzzle here. So I'm going to divide both sides by 2. And now this matches this exactly. So we're going to have our integral in terms of u. So we're going to have 1 over u. So say 1 over u. And we're going to replace the x dx with times du over 2. Now remember, these are all multiples, so I'm just going to pull 1/2 out front just to focus on what I really need to focus on. I mean, the 1/2 is important, but, and we know that the antiderivative of 1 over u is the natural log absolute value of u plus c, and then we can back substitute our expression for u plus c. So a lot of times when the denominator is the inner function, you're going to end up with a natural logarithm as your answer. And that denominator is going to be in the natural log. Let's see. I just want to remind you, like 4 over x squared dx. Really simple function, but it can be deceiving. We're not going to use u-substitution here. This is the integral of 4 times 1 over x squared dx, which is the same as the integral of 4 times x to the minus 2 dx. Okay, so remember, with this case here, we're not going to bring that up as x or u to the negative 1, because if you're adding 1 to integrate, you're going to get that variable to the 0 power, which is 1, and that's an issue. So only with, you know, powers of 2 or higher in the denominator, you would bring it up as a negative exponent. And I'm going to pull the 4 out. and I'm going to focus on this. No u substitution required here. I don't have a composite function. I'm just going to use the reverse power rule. So if I integrate this, I'm going to get x to the minus 1, right? And I'm going to add 1, so I get x to the minus 1 over negative 1. If I clean that up a little bit further, I'm going to bring that negative out front, like so. And then to simplify it all the way, it'd be negative 4 over x. Capiche? So be careful with that. It's not u-substitution. Let's see. What else can we do here? I'm going to look through your book, find some examples. Okay, another example, and I know we did this one in class because I remember it. I don't remember much these days, but this I remember. So it's the integral of x squared secant squared x cubed dx. And again, you know, you might want to rewrite this as secant squared of x cubed times x squared dx. Because, again, you're going to want to replace something dx, whether it's just dx by itself or something multiplied, something else other than a 1, multiplied to dx with your du. So it helps you see it a little bit better. So what's the inner function? Well, I've got parentheses here. The outer function is secant squared of x. So the inner function is x cubed, so I'm going to let that be equal to u. So I know that the derivative of that is 3x squared dx. Now the x squared dx matches here, but the 3 is an issue, so we're going to divide by the 3. And now they look identical, and so what that means is that I can write a new integral as secant squared of u times du over 3. And that means I can bring that 1/3 out and focus on secant squared of u du. This is an easy antiderivative. We know that the antiderivative of the secant squared is the tangent of u plus c. And if I back substitute, I'm going to have the tangent of x cubed plus c. This is awesome stuff. Oh, let's do this one. This is number 6 on page 342. Now remember, George Best tells you, hey, let this equal to u. On your test, you got to figure it out. If it's a u substitution type problem, if it's a composite in your integrand, you're going to have to decide, you know, what your u is, because George isn't going to tell you on the test. Okay, so this is 2x plus 1 squared. Came out kind of terrible. Let me rewrite it. Integral of 1 over 2x plus 1 squared dx. Okay, so, you know, you might think, well, there's a denominator, so I'm going to let this whole thing squared be my denominator. But you're going to see, let's just do it. If u is equal to 2x plus 1 squared, then du is going to be equal to 2 times 2x plus 1 to the 1 times 2, or 4 times 2x to the 1. And you don't even see that anything remotely close to that being multiplied to dx. Okay, it's a 1 times dx. So that should be a red flag. We're going to do like this. We're going to let the inner part of, or what's inside of the parentheses, be u. So du is 2 dx. Well, I've got a dx here and a dx here. Here I've got a 2, here I don't, so what do? We divide by 2. Okay? So now what I can do is I've got this integral as 1 over u squared times du over 2. I can pull out the 1/2, and I'm going to write 1 over u squared du. Well, I don't know how to integrate that, but if I bring that up as a negative exponent, I can use that reverse power rule, meaning I'm going to add 1 to the exponent and divide by the same exponent, right? So I've got 1/2, and now if I integrate this thing, I'm going to have u to the minus 1 over negative 1 plus c, and I'm just going to combine that negative 1 with the 1/2, And I can leave it like this and back substitute, so I can write it like this. What was u again? 2x plus 1. Or I can go ahead and, you know, write it like this if I want to. Oops, sorry. Getting to the end of the paper, so I apologize. Okay? So a lot of times when you have a denominator, the denominator will be what u is, unless it's got like a square root or parentheses in it. If it has a square root or a parentheses in it, generally we'll let the u be, and now this isn't 100%. I mean, it depends. You would have to play around with it here and work it out to see. And if you take the derivative and you get something weird that you don't see in the integrand, then that means, you know, go try a different route. But anyway, generally, if it's parentheses raised to some power or some really weird stuff in a radical, it's usually the stuff inside the parentheses or the radical in that denominator that we assign to u. Let me see if I can find another one really quick. I'm looking, so bear with me a second. Okay, here's one. Integral of x cubed over 5 minus x to the 4 squared dx. Okay, so again, if I let this whole denominator be equal to u, I have to use the chain rule to take the derivative. So I'm going to have 2 times the stuff inside to the 1 times the derivative of the stuff inside. And it's going to get ugly really fast. So, I mean, that might be correct. It may have to get ugly and I might have to clean it up, but chances are I'm going to try just the stuff inside the parentheses. And, you know, you can kind of mentally see what happens. If you take the derivative mentally of the stuff inside the parentheses, you're going to get 4x cubed, and you've got an x cubed there. So that tells you you're on the right track. Okay, so let me just try and readjust. Looks like it's getting blurry again. This thing's getting on my last nerve. Okay, so du is going to be equal to negative 4x cubed dx, right? And again, I have x cubed dx. I don't have a negative and I don't have a 4, so I'm going to bring them both over by division. And again, you know, to help you think about it, you can write it like this. So you see, I'm replacing this piece with du, and I'm replacing that with 1 over u. So my u integral is going to be 1 over u squared times du over negative 4. I'm going to bring out that negative 1/4. I'm going to rewrite this as u to the minus 2 du, and again I'm going to integrate that because it's really simple. It's going to be u to the minus 1 over negative 1 plus c. Combining this with this, I get a positive 1/4, and I'm going to back substitute, and I can write it, I can write it like this, or again I can put it like this if I want to. Either way is fine. Okay, so that should get you through for a little bit more practice. I hope you study and I hope you do good tomorrow. I'm sure you will. Have a good night.